Yeah, thank you. Okay, so let's first say what I mean. So for gamma, gamma 1 of n, so this is about the modular curve y1 of n. And this is a smooth affine curve. And its most important property is that it parametrizes curves with n torsion points, points of order n. So for any field k of characteristic 0, the k rational points on this curve correspond to the pairs of pairs EP, where E is an elliptic curve over k, and P is a point of order exactly n on that curve, and then, of course, up to isomorphism. There's also a curve x1 of n, and this is just y1 of n, but then made into a projective curve, so there are some extra points added, which we call the cusps. And I put the one up on top. Sometimes you see the one below, and often people mean exactly the same curve over Q that I mean here. Okay, so the group of modular units from the title, that is the group of algebraic functions on this affine curve that have on this whole affine curve no poles and no zeros. In other words, it's functions, meromorphic functions on the curve x1 of n, such that the divisor is completely supported at the cusps. Now the main result for this talk is that a group of, or a set of generators of this group. So this group, of course, contains the constant functions, so that's just q star, and the group modulo q star is freely generated by, well, roughly the defining equations of the other curves, y1 of n for n smaller than n over 2 plus 1. And of course, this doesn't make sense before I tell you that all of these curves are in some kind of affine space. One space, one surface in which all these curves are, and then the defining equations of all these curves will miraculously generate the group of units on this other curve. Now, before I go to the detailed statement, let me give some potential applications. Now, I don't know anything about coding theory, but it was in the title of the conference. So let me just say that modular curves are used in coding theory. They have many points because of the cusps over finite fields. I think that is the reason, but I'm not entirely sure. Now, some other reasons to be interested in this. Well, these modular curves, they are important in mathematics, and if you have small functions, then they may give you small models of these curves. Also, these modular units, if you evaluate them in CM points, then you get units in abelian extensions of imaginary quadratic fields, so this is good for number theory. And then if you have small modular functions, and I hope that among these modular units there will be some candidates for this, then they may allow you to speed up complex multiplication constructions, which are used again in number theory, so for example constructing Hilbert class field of imaginary quadratic fields, but also in cryptography when you construct elliptic curves with a given characteristic polynomial of Frobenius. So these are just some potential applications of this group, and let me now go to the detailed statement of the result. And for that, well, let me first propose this ambient surface that I'm going to use. For any field k of characteristic 0, I let A of k be pairs, well, just as before, E an elliptic curve, P a point on E. But now, let's say the order is not 1, 2, or 3, but I'm not going to require the order to be exactly n. And then I take these things up to isomorphism, and then y1 of n is just the sub whatever in this A described by the equation. The order of P has to be exactly n. Okay, so now I'm gonna give a model of this A, make it into a surface, and this is called the Tate normal form. Every pair E, P, where P is a point not of order 1, 2, or 3, can be uniquely written as in the form E is y squared plus 1 minus c times x times y minus b times y equals x cubed minus bx squared, where the point P is the origin. Okay, I'm gonna let D be the discriminant of this, and let me now prove this state normal form for those who have never seen it before. It's really a nice short proof. You start with a general Weierstrass equation for whatever elliptic curve and point that you have. So y squared equals y squared plus a1xy, etc. Then the first thing you do is you translate this model, so you add some constants to x and y to move this point P to 0, 0. And that makes, because this point is on the curve, that makes a6 equal to 0. So we get rid of a6. Next, well, I required that this point does not have order 2. So 2 times the point is not the point at infinity. And that means that there's not a vertical tangent at that point 0, 0. So that means that a3 is non-zero. And because of that, I can add some multiple of x to y to make a4 actually equal to 0. So I cross out a4 as well. And I go on. I also said 3 times the point is not the neutral point. So that means that at 0, 0, there is not an inflection point. The tangent there does not hit it with multiplicity 3. And because of that, we get a2 non-zero. And that allows us to do a scaling of x and y that makes a2 and a3 equal. I just call that minus b. And then I call a1, I call that 1 minus c. And then I have this, this state normal form. And if you know what all the possible isomorphisms of elliptic curves in Weierstrass form are, then you know that these transformations are all that you're allowed to do with elliptic curves. So that means that this state normal form is actually uniquely determined by the isomorphism class of E and P. Now, because of this, A of k, so the k as defined up there, is just it's the point in the affine plane over k with d non-zero, where d is the polynomial in B and C that gives the discriminant of that state normal form up there. Okay, so now I've made this A actually into an affine surface. It's a subvariety of the affine plane, and since y1 of n is an irreducible curve over Q, in that surface I actually get irreducible polynomials fn inside the polynomial ring over Q generated by B and C, such that y1 of n is given by the equation f of n is 0. So these f of n's will be the defining equations of y1 of n, and all in one single affine plane. Okay, so up there in gray is what I had on the slide before. And now I just let B be B modulo Fn. So capital B was one of these polynomial ring generators. Little b is just capital B modulo Fn. And little fn will be capital Fn modulo Fn. So this is a capital F small n and then capital F big capital N. Okay, so now one thing to notice is that actually these functions that you then get, these Fn modulo Fn with different n's, they are modular units for y1 of n. So they are in this group of modular units from the first slide. So what did that mean? That meant that this is a rational function on there. Well, of course, it's given by a polynomial, but also it has no roots and no poles on this affine curve y1 of n. Well, to see that it has no poles, that is really easy. It's a polynomial, so all of the points where it takes the value infinity, those will be at infinity, and we're talking about something inside the affine plane. So there are no poles in the affine plane, hence no poles on A. And if there is a 0, well, that would correspond to a pair EP, some pair elliptic curve and a point, where that point, well, it has order n because it's a point on the curve, and it has order n for the different n, since it is a zero of this function fn. Now, of course, the order cannot be both n and n. So here we have all of these functions, which are actually modular functions, and it was observed by Maarten Derickx and Mark van Hoeij a while ago that actually for n up to 100, capital N up to 100, this whole group was just generated by, well, these functions fn, which we can only do for n greater than or equal to 4 because of the restriction on the order. To get the Tate normal form, we had to have order not 1, 2, or 3. And then these two more functions, b, which was the polynomial ring generator, and d, which is the discriminant of the Tate normal form. So these functions generate that group, at least for n up to 100. They observed this, and then they conjectured this in general. They presented, or Maarten Derickx presented this conjecture at ANTS in 2000, when was it, 12? And so this is the result that I want to present in this talk, a proof of this. Now here are n over 2, rounded down functions, and I'm saying that this group is generated by them. Well, actually, it's known that the rank of this group is exactly that number. So it's really freely generated by these functions. So it's really a basis of the set of functions, which is, well, I found this very strange. You have these infinite set of functions, and you just take the first few, and it generates the whole group. Okay, the first step towards proving this is looking at division polynomials. These are division polynomials that were also in Drew Sutherland's talk in the previous half hour. So if we take any general Weierstrass equation, E, let's say it's smooth, so let's say it's an elliptic curve, over a field of characteristics 0, and we take any integer n, then we get a polynomial psi n, which you can define as n times the square root of this product over all the n torsion points, x minus x of that n torsion point. This is actually, you can take this square root, and well, there's a good way to choose the square root, and you will get an element of this ring inside the function field of this elliptic curve. So that's the ring generated by the coefficients of the elliptic curve and the coordinate functions. So, okay. And what's so nice about this is that psi n of a point P is 0 if and only if that point, well, n times that point is 0. So if and only if n is a multiple of the order of the point. So this is that division polynomial, and now I'm going to evaluate these things in the Tate normal form. And okay, so we take the Tate normal form, which is an elliptic curve where the coefficients are in this polynomial ring with generators b and c. I evaluate these division polynomials in this Tate normal form, and I get, well, the division polynomials, of course, become polynomials in b and c when you do that, where your b and c correspond to an elliptic curve with a point that has order dividing n if and only if the b and c are a root of pn. So, in particular, since fn corresponds to having an order exactly n and pn corresponds to having order a multiple of n, fn will be a divisor of pn, and actually you can show that fn is the unique new factor. So if you write down this sequence of pn's, you get one new factor each time, and the unique new factor, we call it pn, and the group generated, well, the group from the theorem on the previous slide is exactly the same as the group if you use the p's. So we're going to use p instead of f from now on, and the theorem is just is generated by this with p. Now these functions p, or actually these division polynomials, they have a nice recurrence relation. So this is a way of explicitly writing down all these equations for these modular curves and all of these modular units on them. There's this recurrence relation that the division polynomials satisfy, that's the top line. And there are two special cases of that. If you do some substitutions for m, n, and k in this complicated recurrence relation up there, you get two different recurrence relations, one that gives you all the odd number terms and one that gives you all the even number terms. Here are just a few very easy curves. Psi of 0 is 0, psi of 1 is 1, and psi of 2 is that thing over there. Now we can do this substitution of the Tate normal form in there. So we put p's everywhere. P0 is 0, P1 is 1, P2 is minus b, and you can use Sage or whatever you like to compute some more terms. P2 is minus b cubed, P4 is cb to the 5. And now the recurrence will just give you all of the other terms, or Sage could give you these terms as well. For example, P5 is, you fill in the recurrence and then you get minus b to the 8 times c minus b. P6, you can do it as well. P7 and P8, here are just some examples. And now in blue, I highlight these new factors. So these are the Fn. So f of 4 is c. So that means that the point has order 4. The point corresponding to b, c has order 4 on the elliptic curve if and only if c is equal to 0. The point has order 5 if and only if c is equal to b, because f5 is c minus b. It has order 6 if and only if if b is equal to c times c plus 1. And that gives us it gives us a defining equation for y1 of 6. So here's an example. Y1 of 6 is given by f6 is c squared plus c minus b equals 0. And the units of that by the theorem that I'm going to prove, this group of units is q star times b and d and then p4 up to p of 6 divided by 2 plus 1, which is also 4. So it's just these three. And I can compute these three explicitly. I get, b was c times c plus 1. I compute the rest as well, and I see that this group is generated by c and c plus 1 and 9c plus 1. So that's just an example of that. And now I'd like to go back to the proof. So step 1 was using the division polynomials. Step 2 is to look at complex elliptic curves. So there's a complex uniformization of this modular curve, and that's exactly what I'm going to use now. So there's SL2Z, that's 2 by 2 integer matrices with determinant 1, acts on the upper half plane by this standard modular action up on the right there. And if we let gamma 1 of n be the matrices in SL2Z where the upper right entry is divisible by n, then the set of orbits for this action of gamma 1 of n is exactly the set of complex valued points of this curve y1 of n, where to a point tau in the upper half plane you associate an elliptic curve in classical Weierstrass form. That's the e tau over there, 4x cubed minus g2 tau x minus g3 of tau is y squared. So that's the elliptic curve, and then the point comes from the Weierstrass p function. You take the point 1 over n tau modulo some kind of lattice, and you evaluate the Weierstrass p functions in them. So that gives you a way of parameterizing this modular curve. And in fact, the group that I'm interested in, the group that I'm talking about in this whole talk, is a group of holomorphic functions from h to c that are nowhere 0, that are invariant under the action of gamma 1 of n, that are meromorphic at the cusps, and whose Q expansion has coefficients in the rationals. So that's the group that we're looking at. And now I know a little bit about the division polynomials also in the complex setting. So if you take the division polynomials for this classical Weierstrass equation E tau, then it has something to do with the sigma functions. The exact formula is not important, but if I combine this with an explicit rewrite between this classical Weierstrass equation and the Tate normal form, then that gives us a new way of writing this group that we're looking at. I take these very old Siegel functions, h, a, 0, which are somewhat given actually by a Q expansion. For a rational number between 0 and a half, I take h of a0 of tau to be this complicated function that really just is, well, if you write it out, a Q expansion. Then the writing out, of course, there are some tricks involved that are well, and some definitions in between that are too complicated for a 20-minute talk, so I'm just going to give the result, which is that the group generated by all of these things is exactly, well, it's a subgroup of the group generated by these Siegel functions for A ranging from 1 over n to, well, k over n, where k goes up to n over 2. It's a subgroup of that. It's not exactly the group generated by all of that. It's a subgroup of that given by the number of factors has to be divisible by 12. And if for each factor you take k squared and you sum that, then it has to be divisible by, well, by n if n is odd and by 2n if n is even. So this is another way of writing that same group, and then that means that the theorem that I mentioned twice before, that the theorem is now equivalent to proving that the group of modular units is q star times exactly this group S of functions of this form. Okay, now these functions appear in a theorem of Kubert and Lang that is almost what we want. It works for y of n and over the complex numbers. Well, that's a much bigger, the group of units for that is much bigger than what we're looking at. So actually, you'd expect that theorem to be stronger, but that theorem is actually not strong enough because it only works up to a power of 2 index. It only proves that if you look at this map from S times q star to, or the analog of S, what it would be for y of n, to this group of modular units, then you get an injective map whose image has an index that is a power of 2. So it's not strong enough the way they give it, but step 3 is to take some ideas of that proof and to use it here. So the first thing is that we're going to prove that every function, every modular unit, can uniquely be written as a constant times a product of these Siegel functions where the exponents are not integers yet, but at least rationals. And then by a rational power, I just mean just take any root. I don't care which root you take if you have a denominator in your rational numbers. And then the next step would be proof that actually these exponents are always integers. And then a final step will be, no, well, there are these two more conditions up there in the definition of the group S. The first is that this number of factors has to be divisible by 12, and the other is that sum of k squared has to be divisible by something as well. So that's step 4 to prove that. Okay, so step 3 is about Q expansions. That is what Kubert and Lang use. And for simplicity, I will just assume that n is odd. The proof in the paper works in general. Here's again the definition of H up there. Then let's look at this map S, map from S to these modular units up to constants. Then the codomain, well, that is the rank of that is, and then the first equality there should actually a priori be less than or equal, but anyway, it's a number of cusps, a number of Galois orbits of cusps minus 1, because the number of degree 0 divisors is the number of Galois orbits of cusps minus 1, and that you can compute to be exactly n over 2 rounded down. Now I claim that the image has this same rank, and if once we have that, then we're done, right? Then the map has to be injective, and the co-kernel has to be finite. So how do I prove that the rank is exactly this number? Well, for that I just prove that all of these Siegel functions that I gave are multiplicatively independent. And the tool for this is just look at the Q expansions. And it's easier to look at these Q expansions by forgetting this leading term. So you get Q expansions that are 1 plus higher order terms just by dividing out all of that, well, the constant I and the Q to the power whatever, you divide all of that out, it's gone. Then you have this thing after the equality sign left. And then you just look at the main terms. So you start with a 1, then plus Q to the A, and then the rest is higher order terms. Big O of Q to the 1 minus A. Okay, so as I said, I'm going to show that these functions are all multiplicatively independent, even modulo constants. So that means that if we take e, a vector that is non-zero, and then I take the product of h to the power e, that then we cannot get a constant out of this. Now, suppose e is non-zero, then we could take k0 to be minimal, with the minimal number with e of k0 is non-zero. And if I do that, and I take f, where the star again means divide out by the leading term, so you get something that starts 1 plus whatever. Well, this f star is a product of the h stars to some powers, and the h stars are the things over there, the 1 plus q to the a plus higher order terms. So the dominant thing there, when you take the product of all of that, is you get 1 plus e of k0 times q to the power k0 over n. That's how it starts. And of course, this, since e of k0 is non-zero, this is not going to be 1, so f is not going to be constant. Okay, so that is the proof, right? So that means that this S, it has to have rank, full rank, so same as the number of generators that we had, n over 2, and then we are done. This image is, well, this map is injective, and the image has finite index. That was the first step. Then the next step is to show that these exponents...
Skip some steps.
Yeah, exactly. Well, I think I should, yeah. I started 5...
You are
10?
talking for 27 minutes.
20, okay, then I'm done, right? So it's a 20-minute talk. Well, well, okay. No problem. So step 4 is just like step 3, but there's one cool trick, and here's a summary. So here are the 3 statements that I had. Step 1 was connect the things, and then here, step 3, here's the short summary of it. Use the Q expansions and Gauss's lemma for power series, and finally use the action of gamma 1, and you prove that actually this thing is generated by all of that stuff. Now I'm working on y of n, y0 of n, and well, more or less, I think I'm going to go past these 3 things in order, or maybe just stop after the first. But I'm now working on y of n, using some generalization of these division polynomials. Sorry for going over time. Thank you.